Hello, my name is Elise Franchuk, and this is going to be my third assignment submission for Comp 444 on embedded and robotic programming. So, for this unit, or for this assignment, I will be reviewing chapters 10 to 11, and we'll start with controllers. So, control theory, it's concerned with feedback, feedback from the controllers. Basically, it's a framework how to use parameters to make effective controllers. We're concerned here with desired state, such as where does a system want to be, and this is broken into two areas, achievement and maintenance. So the error, this is used to calculate the difference between the desired and current state. For example, you are 20 kilometers away. You have traveled 10 kilometers so far. The distance is 10 kilometers where you need to be. Direction of error. This is used to minimize error towards the goal. Distance, like it's minimizing distance, level, pressure, whatever you're trying to control. And then we have the magnitude of error, how much distance you have to the destination, which we talked about earlier. Else if statements can be used for basic feedback controller to program behavior. And sampling rate is the rate at which errors are computed. Calibration is necessary for effective feedback controllers as well. And we have a picture here on the side of a very basic feedback controller. However, it would not be as efficient as the following ones. So feedback controllers, more on that. We have proportional derivative control and proportional integral derivative control. What they have are different ways of calculating feedback. Some are smoother than others. Obviously, proportional would be the least smoothest because it has less data points to work with. And we have important things we can discuss, such as gains, proportional gains, and actuator uncertainty. And these are all just things that, again, are computing error. How much things we have to work with to compare and control where we're going or how we're controlling the robot. So we have integral control. This basically keeps track of the errors. It has a comparison, like a history to compare to, rather than just constantly reacting to stimulus. This system integrates error over time and fixes or compensates them once a certain threshold is passed. And this is where steady state errors are introduced. Now we have open and closed feedback controllers. Closed loop control, this system is provided with the error as the feedback, and versus the open control or feed forward control, they're basically the same thing. It does not use sensory feedback. Environment needs to be very predictable, and it's better for automation. It's better for repetitive and state independent controllers. So we have a picture on the side here of a feed forward or open loop. Once again, it does not use sensory feedback. So we have control architecture. This is the guiding principles and constraints for creating a robot control system. It helps programs predict overall output behavior and makes them a little more accurate. We have robot control. So robot control requires signal processing, hardware, and computation. All three of those need to be usually led by specific teams. However, we'll take a look at what exactly they do here. We got some basic definitions of an algorithm, solving a problem using finite procedures, like mathematical functions, same principle. And we have a robot that has their control implemented in software is more versatile. This is sometimes more useful than specialized hardware or architecture. This is true because if a change needs to be done quickly, it could be done in the software rather than changing the entire hardware, which would be very expensive and also very time consuming. We have common architectures we can use. We have deliberative, reactive controls, hybrid controls, and behavior-based controls. Each one is really used for different things, and the things that we need to look at in these architectures are the time, modularity, and representation. So a little bit more information on control system architecture, such as the three things that we pointed out. We got timescale, how fast the robot responds. In a later example, I'll have a robot. Its response time is limited. However, it is definitely an example of timescale. We have deliberative control. It looks into the future. It's more predictive rather than being a automated system. Then we have reactive control. So this responds to immediate real-time demands. Then we have hybrid and behavior-based control. They're similar but a little bit different. For example, hybrid control combines long and short time scale of deliberate and reactive controls, but behavior-based, it does it differently, and we'll get into that later. It really has to do with how it just computes the data. So representation, how information is encoded or stored in the control system. It's how it deals with it internally, essentially. Modularity, how the control system are separated into modules, and are they sequential or parallel? Basically, how many things can react at the same time? Can two parts can two sensors be listening at the same time rather than a sequential program that runs one by one? If the controls are behavior-based, 3 or more modules are parallel. So the things we can really start to question is, what kind of robotic control system are we looking for? Is there a lot of sensor noise that we need to be cognizant of? Is the environment predictable? How much information is needed exactly from the sensors? And how fast does the system need to react, if it needs to react at all to certain stimulus? So I'm going to quickly go through the projects I did for this assignment, and it was really 2 projects with the last second and third combined together. However, let's get on with motor basics. So this uses the TB6612 FNG driver motor, and basically what this is an integrated circuit that allows easier manipulation and control and granular control of motors, specifically the stepper motors. What the voltage in pin is able to do is it could either take electricity from a battery, or it can output directly the electricity without any limits, or at least to whatever the Arduino can supply to the motors, as they require a lot more electricity to move. I think it's like 9 volts. So gear motors, they can turn in any direction, and the speed is also controllable with pulse width modulation. So for this assignment, I decided to actually try out the 433 megahertz sensors, so the transmitter and the receiver, for the communication. And it worked, and it was interesting to program and use. I used the virtual wire library to program everything, but it wasn't as useful. It was more sporadic and unreliable for the next exercise. So I also tried with a potentiometer, and it was given consistent results, but as we'll see soon, it wasn't that reliable. So this was the most time-consuming but funnest project so far, and it was the remote control and autonomous robot. Here I decided to use infrared instead of radio frequency. Infrared is not emitted as much, and it's more reliable, but also I found that it may have been the antenna or something that I was working with for the radio frequency that just was causing the transmitter and the receiver just not to communicate very well. I ended up designing the body of the robot. It was a very basic design. It looked kind of cool, but overall it seemed to have worked. So there's that. In the front of it, I decided to put a wheel from a roller chair. It worked. It looked good. Now for that, for the autonomy, so the autonomous robot part. This is one step away from remote control, and this was done with a very basic else-if statement, else-if logic. And I'll get into more of the code. So basically what's happening in this code here is it checks if there's a warning, and this warning is sensed from the distance sensor. If it's if there's something in front of it that's less than 20 centimeters away, it's going to give a warning. So if there's none, it'll keep driving forward. However, if there is, it's going to go back, and then it's going to turn right. And then hopefully by then the warning is gone. If not, it'll just keep redoing that. Lastly, I'd like to discuss some ideas for the final project very briefly. I'm thinking of using the GPS, gyroscope, accelerometer, and using it for a semi-autonomous drone. And I think it's going to be an interesting project to pursue. It's going to be a new challenge, and definitely it's going to take a lot of research into different concepts. And I think it's going to prove a lot to both on the programming side, but also on the electronic side and electrical side. So this was my presentation for assignment 3. Thank you for watching. My next post will be on the final project. So I hope you stay tuned, and see you next time. Thank you for watching.